Hello and welcome to another episode of the AI Digest. My name is Joaquin Melara. I'm the host, and with me today is Dr. Giuseppe Futia. He is a AI consultant and published author. Giuseppe, you are based out of Italy, is that correct?
Yeah, I'm currently based in the northwest of Italy, in particular in a city that is called Turin. That I invite everyone to visit it because it's one of the most wonderful place here in Italy.
And quick question, what kind of food is there available locally?
I think that we specialize in meat, but we also a typical dish that we have is called Piedmont fried, which actually includes a lot of fried fish, from fish to vegetables to meat
Hmm.
to fruits. Yes, it's really powerful, but it's really tasty. So it's typical of this region of Italy.
And out of curiosity, I'm not gonna take up the whole conversation on food because I'm hungry. But how's the focaccia bread there?
The focaccia is really nice, but it's not typical from this area of the
Uh,
Italy. It's more typical from a region that is called Liguria. That is, I'm sort of it's in the sea. It's always in the northwest, but it's in the sea. And I have been there this weekend, and it was great. I ate a lot of focaccia, I have to say.
Wonderful. Well, thank you for the culinary little lesson there. I will visit Italy, and now I know to go get fried seafood, and uh, I know where to get the focaccia. So, presently, you are gearing up to launch a training program on knowledge graphs and graph neural networks. Is that correct?
Yeah, exactly. My plan is to deliver in the next months a course that, in some way, include both these topics. That apparently seems quite far, but I hope that during our conversation we will understand better the connection, right, between knowledge graphs and graph neural networks.
When I say you're an AI expert, you're a consultant. I mean, you've been doing this for quite some time. You've been doing research. You've been in the development and industry of these solutions, and you've also been heavily involved in the technical communication and authorship of how to present these ideas in an accessible way through conferences, through public talks and trainings. So I'm very much excited to hear from your mind because even in the dialogue that we had before starting the recording, you were quite lucid and just very clear in how to represent these very complex ideas. These None of these ideas by any means are simple in their own. You're putting them together, and I thought it would have been a little scary, but actually, you made it very enjoyable.
Yeah, definitely. That's what I like to do, right? I would like to explore all these technologies, including large language models that are now very on the hype, right, of the discussion at any level. And all these technology have a common blueprint, right? Because they are all technologies that are created to incorporate the human knowledge into machines in order to automatize some specific process. So I would say that both in my academic and industry experience, this was the most exciting part, right? Try to identify the connections and the links between all these technologies that are developed for a unique purpose at the end of the day, right? In terms of incorporating machines with with the knowledge that has been developed by humans in all the history, I would say.
Hmm. And you've applied these technologies particularly in the domain of healthcare, such as public policy support, and also in the space of cultural heritage, such as open archives, right?
Yeah, definitely. I successfully, I would say, employ this technology for a middle-sized non-profit company here in Europe that is focused on developing policy support directions in the healthcare domain. And regarding the cultural heritage and the, let me say, archive domain, I worked with a US nonprofit that is the Rockefeller Archive Center, whose main goal is to gather all information that are related to the funding process of the Rockefeller Foundation, right? During my experience, I really find interesting information in extracting, in particular, conversations, right, from old documents of the beginning of the 20th century, right? And the idea was to extract this conversation to understand the dynamics between the Rockefeller Foundation officers and the researchers from all over the world, in order to understand which are the key conversations that in some way led to a specific funding of a specific research topic and a specific research scientist, right? So it was really excited. And in that case, we adopted the large language model to extract this information from this natural language content, and then using knowledge graph to model this specific extracted content to get what the domain expert were interested in, right? So basically understanding these dynamics that potentially could lead to a specific funding from the Rockefeller Foundation. So it was an exciting project, and I think that it will continue in the next months. And hopefully, I would like to provide some further insights that we will get during this collaboration.
Interesting. That seems like a non-trivial exercise, given that you're scanning text documents and language changes over time, and there's no continuity sometimes of context between different text languages. So you have to really find a very smart way of analyzing what are the key actors in a decision-making process. How do you model that? And through time, track how that those actors are changing their minds or adding to the decision making process. It just seems to me like a very complicated, but you know, it just seems like a very complicated problem to solve, but interesting. Let me talk about the technologies that you specialize in. You've been working with ontologies, knowledge graphs for a very long time, and you mentioned now with the rising popularity of LLMs and graph neural networks as well, you've been focusing your attentions on figuring out how to reconcile these three major technology groups. Um, is there anything that you'd like to say about how what would led you to be interested in this regard, or
Yeah, definitely. Because as you said, Joaquin, this technology are extremely useful, apparently for different purposes. But as we mentioned at the beginning of our conversation, that can be combined in a fruitful way in order to get specific business goals, right? Um, I mean, I would like to start with knowledge graphs, right? Because I think that could be a good starting point, because knowledge graph can be considered a really flexible structure to represent connections between different elements. And the knowledge graphs in the historical perspective could be seen from three different point of views. There is the point of view of knowledge representation, in which the key idea was to try to capture the complex knowledge in a specific domain. And the interesting thing is that the initial promoter of this knowledge representation, or we can say ontological perspective on knowledge graphs, have been philosophers and lawyers, right? Because they were really interested into translating the complexity of the knowledge of their domains into something that could be more concrete in some way. This is one perspective, right? So the knowledge representation that we are able to encode using knowledge graphs. The second main perspective is related to the database vision of knowledge graph. So in this case, knowledge graph can be considered as a sort of containers of information that can be potentially queried in a very deterministic way, right? And consider the flexible way in which these knowledge graphs can represent information, enable the opportunity of query this flexible knowledge. It's really powerful, right? Especially for business purposes that requires very deterministic responses from their systems. And there is a third, but not less important perspective that sees knowledge graph as a sort of a data structure on which we can perform analysis and apply machine learning techniques. And this is the perspective in which the graph neural networks come to play, right? Because in the last year, we started to see knowledge graph as a repository information in which we can perform some specific tasks that derive from the machine learning, including, for instance, classification of nodes or classification of graphs. And we can also see some tasks in the context of limb prediction, right? So basically, we want to understand if one node can be connected to another node and according to which probability, right? And graph neural networks play a fundamental role because in this context, because they have been natively modeled and defined in order to extract specific patterns and regularities from this graph structure. And if I can, I would like to add some specific examples in which knowledge graphs have been applied successfully, right? In the last year, there have been 2 papers. One paper released by LinkedIn and another paper released by Spotify, in which both these companies successfully applied graph neural networks on top of knowledge graphs they created for responding to their specific business purposes, right? So, for instance, in the case of LinkedIn, they modeled the information related to the members, to the companies, to the groups, or also to the posts. They define the relationships between these entities. For instance, if a person put a like in a post that has been released by a company, and they run graph neural networks in order to improve their recommendation part in terms of jobs from a company to a specific user. And Spotify try to exploit the same principles, right? They obviously include information like related to podcasts or to audiobooks, and they exploit graph neural networks in order to improve the recommendation systems of this content, right, to the users. And they reached a pretty good success, right, because they measure a sort of increasing in terms of applying of from the user to these specific contents, right? So the users liked and decide to buy, for instance, these specific contents on the platform. And for Spotify, there is another interesting case that we can call like model transferability, because since the beginning, they have a lot of connections between users and podcasts, right? While the audiobooks were a sort of pretty new content in their database. So basically, they did not have a lot of information regarding the connection between these users and these podcasts and these and these audiobooks, right? Because they were quite new content. So they were able to successfully apply graph neural networks also in this challenging context, right? And in this specific situation, they also include large language models. Because if you consider, for instance, the content of the podcasts, of the content of the audiobooks, they can clearly successfully encode it using large language model, right? Because they have been natively developed to process language and to extract interesting features. So they successfully combine these two technologies, large language models and graph neural networks, because they encoded the textual content of podcasts and audiobooks. So basically, they apply a sort of enriching process of the features of these nodes, and then they apply graph neural networks to improve the recommendation system. So I think that this is a typical example is a successful business case in which they were able to exploit the potential synergies between all these technologies, right? So basically, they built a knowledge graph on top of their key entities and relationships. They apply large language model to encode the textual content that was related to these entities, in particular podcasts and audiobooks, and then they leverage graph neural networks to improve their recommendation systems based on this representation of their nodes in the graph. So this is pretty exciting, right? Because you can see that for some business purposes, you cannot just exploit a single technology, but you have to extract the best of each technology to reach your goal.
Yeah, I that's fascinating. You pulled together a couple ideas that are floating around in my head, and you made it a bit more clear how they fit together. Um, one key word here in the podcast is AI, and there's a lot of confusion around that word because anything to do with computers or any sort of automatic response from a computer, the general public views as AI. But the way that I've been viewing at it is within my involvement in event management for the last 3 4 years, and in space of knowledge graphs and knowledge representation and reasoning, I've come to distinguish that there are two kinds of buckets for AI, which is the symbolic, where you have ontologies that you shape ideas, concepts, give meaning, give data, metadata of what it represents in the world. And then you have the statistical AI, which is the classical AI. How do you reason with shapes or decisions that have particular algorithms? And they're naturally complementary because ideas in the world, if you give them shape, those shapes are easy to process if you have a defined algorithm that processes those shapes. So, in the way that you describe the initial layers of modeling knowledge, modeling ideas to give it some sort of representation layer structure, it makes complete sense that you have a album, and the album has metadata like which is the band, when was it released, who is the publishing house of the album, what songs does it contain, what is the genre. It makes sense if you have a series of albums and people engage with that album, how many listens, who likes it, who dislikes it, what comments are on it. You can then apply these machine learning flavors or specialized machine learning algorithm techniques to figure out, okay, we want to maximize this business goal and we have these knowledge shapes. How do we accomplish this task in a seamless way? And now you're saying, which is another non trivial task, we need to ensure that we can accurately describe what is inside of this digital content, digital asset that may or may not have context. But large language models, you can dump out the context in natural language and you can sort of reason what are the main ideas with this statistical uh, model tool to
Yeah,
enrich it, give it more metadata. That's what you're saying, the enrichment process, and give the idea, the concept, more shape, better shape, more defined, more hooks for the algorithm to take shape.
exactly, definitely. Because one of the uh, main aspect related to the graph neural networks that is directly connected to their effectiveness is the features that you assign to the nodes, right? So basically, if you are able to assign a rich set of features that actually are represented in a vector way, then this model can work better, right? And the large language model are naturally good, right, in generating these potentially. This is one of the way in which we can use it, generating these embeddings related to the textual content of these nodes. So you have a rich set of features that you can directly use for these specific network tasks using machine learning. And I want to connect, actually, if you agree, Joaquin, to what you said before, right, about this hype of generative AI. Because as you mentioned, right now, for most of the people, the artificial intelligence is only generative AI, right? Because I mean, I think that it is packaged in a way that everyone can understand, in the sense that the possibilities, right? But the problem is that this type of AI is not enough, especially when you have to take critical decisions. Because, as everyone knows, at least the people that work on this technology, there are some huge limitations, right? Including hallucinations. So basically, the instability on the generated results. And so this is in contradiction with factual knowledge, because if something is a factual knowledge, then you cannot have a hallucination, you cannot have instability, because this is factual. Or there are other issues related, for instance, to the concept drift. So basically, the knowledge um, on which the model has been pre-trained, it's not enough updated, right? So this is another. This can have also a critical. This could be a critical problem that can have an impact when we take a decision, right? And another interesting point is that sometimes when a new model is released, in the documentation or in the paper, you see the expression, "We were able to improve the reasoning of the model." And it's a bit tricky, right? Because is the model able to reason? If so, then we didn't have issues like hallucinations, because the answer, the response of the model will be always the same, because he was able to understand the reason around a specific fact. So anytime in which I see this usage of the language, I'm not so convinced, right? Because the real and the concrete reasoning as a deductive nature, it
Mhm.
can be encoded right now with just a subset of technologies, and ontologies are one of that, right? Because in the ontology, you can encode, for instance, the hierarchical connection between a concept and another concept. You can incorporate in the relations specific features, right? So, for instance, you can say that a relation is symmetry, is a symmetric relation. For instance, a relation like as a sibling can be defined as a symmetric in ontologies, or a relationship can be described as a part of. So basically, a transitive relationship in which you can understand that if you have a connection between A, B, and C, then the connection, you have a connection between A and C if you have a transitive property of your relationships, and so on, right? So in this case, with this specific technology, you can explicitly encode something that can be used for reasoning purposes. Then we can understand if it's useful at all. This is also a debate, right? Sometimes when we work for practical problems, we don't need all this power in terms of reasoning. But in any case, this reasoning is enabled by an explicit definition of some features that we attach, for instance, to the relationships in the case of an ontology and potentially in the case of a knowledge graph. So this is something that should be clarified. I want to say that when you read, we improved the reasoning of this large language model, this is not something that you have to believe at all, right? Because I
Yeah,
don't say that now the model is reasoning. Maybe is able to reason. Is not. Maybe
more
it has been
scientifically
improved.
accurate.
Yeah, yeah, it's accurate. Exactly. We improve the capacity of extract more specific language patterns, but
Mm,
it doesn't mean that
it's reasoning.
now the model is able to reason.
Yeah, there's the reason I work with these two buckets of AI is because it simplifies things very greatly, and just being able to categorize these ideas in a very easy to understand way for the public, it makes sense to look at it that knowledge graphs and these LLMs are both models, right? You can agree to that. That these both of these ideas are meant to represent the world and give shape to reality. But the difference is that knowledge graphs and ontologies are cast in metal. They're cast in something that is defined and well shaped, and there's a lot of considerable amount of time and energy used to build the structure of these models, these I don't know, the blueprints of what reality is. But
Yeah,
the large language models, those three words make me very nervous. They make me nervous in conjunction because model means representation of something.
yeah,
Language is a soup. Language is a thing that evolves, that changes according to who you are, where you are, what time period in the world, what geolocation, what religion, what belief system, what educational level. Language is a crazy word that represents so many things to so many people. So language model to me seems like a fallacy because it doesn't apply to everybody everywhere. And then
yeah,
large language model is a composition of language trying to model what it all means. To me that's crazy because there's no way to arrest that idea in one encapsulation, because if we were to model Italian language and English language and Spanish language, that's going to be a very confused model. It's very confused robot, or whatever way
yeah,
you want to look.
yeah. Absolutely. And regarding this topic of the language, I would like to recall what we discussed at the beginning of the conversation, in which I mentioned the work that we did for the Rockefeller Archive Center, right? One of the most challenging tasks was to defining a prompt and define a set of very specific examples, because we use the large language model in its few shot learning, right, in which we defined a starting prompt to describe the general task, and then we had to define some specific examples from which the model was able to learn what to extract from these whole documents, right? And the problem is that these model have been pre-trained actually, so on documents that are currently available on the web, right? So basically, they are not older, potentially from the 1990, I would say, but I needed to extract information from documents that have been written from the 1920, right, around around that years. And I noticed that the way in which people expressed information was really different, right? They tended to use a more academic and formal way to express also basic contents. So it was not an easy task to find a prompt that was able to extract information from this document, considering that it was trained on web pages and it was the fine-tuned potentially sometimes on code or other specific tasks, right, that are not so close to what we wanted to extract from these documents of the Rockefeller Archive Center. So it has been an iterative process, right? We defined our initial model. Based on this model, we defined a prompt, a model in the sense of a knowledge graph model, right? That included the entities and the relationships that we wanted to extract. Then we try to use this model to drive the definition of the prompt in order to extract the information we were interested in and populate the initial model that we defined with the information coming from these documents. And it was exciting, as I said before. So I would say that, if I may add, Joaquin, uh, just using large language model was not enough, right? We also apply a lot of post processing in order to, in some way, refine and readjust the results of the information extracted from the large language model, considering all the issues that we have defined before, including hallucination, concept drift, also the sensitiveness to the perturbation of the input, resulting in the output. So we needed to apply a lot of post-processing techniques, right? And I think that one of the most exciting post-processing that we did was the entity resolution, because we had this huge set of documents, right? And this huge set of documents mentioned a specific scientist in different ways. So, for instance, they used, in many cases, just the surname or the starting letter of the name and the surname, or sometimes the full name. So we needed to perform a sort of resolution and reconciliation between all these expressions, right? And sorry, large language model helped us to do this process, but it was not enough, right? Because sometimes it was not able to reconstruct the full name of the researcher, of the scientist. And another interesting use case was was related to the situation in which we had the same name for two distinct scientists, right? For instance, when we had Bohr, right? And probably Bohr, the most known Bohr is Niels, but there was also his brother that was a scientist. So in that case, we leverage the contextual information of the knowledge graph, because in order to perform the disambiguation, in the case in which we had the same name for two distinct persons, we used, for instance, the related activity research, the related research activity, right, or the related affiliation. So which were the organization they work for. So by combining this information related to the organization and the research topic the scientist worked on, we were able to perform the disambiguation part, right? And you can easily understand that this information was modeled into the knowledge graph. So we exploited this contextual knowledge, and then we decided how to disambiguate it. So
That
this
is
is another example, right, in which we can create the conditions for a fruitful collaboration, right, between these technologies.
that is true reasoning. That is something that people take for granted because we don't even know how it works or how complex it is as a function. That we are able to take context clues and disambiguate. Okay, this document refers to a person by their first name or their last name or a composition of both or their initials, or a composition of different people that have the same last name but different first names, so they come from the same family, or they aren't related directly but they have the same last name because they were married. There are so many different ways of looking at these proper nouns, real world human construct ideas that shape language, or are driven by the shapelessness of language, that need to be reconciled so that a machine can understand. Because as you said, machines don't understand. They don't reason. They only borrow statistically what may likely be a proper answer.
Yeah, definitely. So in some way, these the conditions for the reasoning should be encoded in an explicit way, right? This is an essential and a pivotal feature, right, in order to enable and develop machines that we can trust. And regarding this idea of the disambiguation, this is extremely important, for instance, in domains such as healthcare, right? We discussed it in our previous during the data-centric AI symposium, right, in which I bring some examples related to the healthcare domain, for example, including the Zika term, right? We have seen that Zika could be used for naming the virus, for naming the disease, for naming the congenital form of this disease. And apparently, these entities are quite similar, but in terms of practical aspects related to the specific goals that you have, there is a quite, I would say, huge difference, right? Because if you want to understand, for instance, the evolution of a pandemic, right, then you want to able to extract information about the diffusion of the Zika virus from different reports, right? Maybe in that case, you are not so interested in all the symptoms that are related to this specific disease, right? Or maybe you can see you would like to monitor the congenital form, right, of these diseases because it can have an impact on the epidemic diffusion, right, of this disease. While if you want to study, for instance, the characteristics of this disease, you want to analyze the symptoms from clinical data, then in that case, you are more interested in detecting the Zika term in the context of the mentioned disease, right? Because you would like to get data for that specific purpose. You want to extract information from clinical data that usually describes symptoms of a specific disease. Because, for instance, you want to develop a library that can potentially use from third parts and so on. So this disambiguation play a fundamental role, and the fact that you have these huge ontologies in the biomedical domain helps you a lot, right? Because, for instance, the synonyms that are constructed and associated with a specific disease, for instance, are extremely valuable because they are supervised by humans. During my activity, as I mentioned, we analyzed these epidemiological reports, right? And I encounter the dengue disease, which can also be called backbone disease, right? And you can immediately get that these strings are completely different, right? And for this case, you need a knowledge repository that includes this information. So basically, backbone fever is synonym of dengue fever. This is useful. And then you can decide potentially, I mean, I would say that large language model, by processing the huge corpus on which they have been pre-trained, can understand, right, this similarity between these, but will not be so structured in an explicit way, right? Because maybe large language model can learn it from the context, but at the end of the day, you need a reference repository like an ontology or a knowledge graph in which this information is directly encoded, right? Because in this way, because you need some factual knowledge in any analysis, in any research activity that you want to perform. So this is also another aspect that should be taken into consideration, I would say.
Thank you for painting that, um, the importance of disambiguation as a core technique in being able to properly use computerized systems. I mean, context again is something that we take for granted, but you're going narrow. You're going at the molecules or atoms or organic structure of a Zika virus, or you're going at a higher level and you're saying the impact of Zika on a person and the symptoms that may concur from that, or that may result, and then you go above that and you're like treatments for Zika, what kind of medication, and you go above that and you go global populations and impact of environmental conditions that lead to Zika because mosquitoes are growing in a particular area, because it rained, because people have poor sanitation practices, or there's no way to eradicate the mosquitoes effectively. Um, all that context is lost in a large language model in some
Yeah,
fashion. So having a molded, very well defined, or maybe not molded, chiseled definition of what it means at which level and what facts it can rely on. That's important for you to be able to understand the explainability of a system as well as rely on its truthfulness and its factualness.
yeah, exactly. Because the ontology, another interesting aspect of the potential opportunities between in try to mix this technology, right, is related to the fact that actually this ontology, obviously under the supervision of the human being, can be potentially be enriched by the knowledge that has been extracted from large language models, right? I would like to make you an example of this. Sometimes in the text of these epidemic reports, I noticed the co-occurrence between two different diseases, right? So basically, one disease was in most of the case a consequence of the presence of these other diseases. And when I try to explore some of the current ontologies in the biomedical domain, there was not an explicit relationships between these diseases. In the ontology, you just could get that both these diseases were diseases, but there were not a direct connection between them. So in that case, potentially large language model, if they are able to identify a specific pattern that is related to the co-occurrence of two different elements, then potentially under the supervision of the human being, this extracted knowledge can be uh, formalized in an explicit way and then used to enrich and incorporated and can be incorporated in ontologies, right? So this is something interesting. This is the bidirectional, we can say, virtuous circle that we can create. So we mentioned that the ontologies are useful for LLMs because they include well-structured and well-defined and factual knowledge that can be used to drive the large language model process. But at the same time, with a bottom-up direction in this case, we can try to identify some patterns in the language because, for instance, there is an emerging trend, right? And then when we identify this pattern, we can analyze it and say, okay, this pattern can be translated in a factual knowledge. So potentially I can decide for my business purpose that these detected patterns can need to be directly encoded in the ontology. So in the future iteration, when the model, large language model, for any reason will not able to recognize this pattern in the text, then we can exploit. We could, we can exploit this knowledge encoded in the ontologies that was able to extract in another uh, time, right, in another frame during the processing phase. So I would say that the opportunities of integrating the opportunities there are a lot of opportunities.
We can so you were saying about integrating these technologies?
Yeah, exactly. And as you can see from this example, we can integrate in both directions, right? So basically, ontology can support inference process and generation process of a large language model, and large language model can be useful to extract patterns in the language that can be encoded as factual knowledge that can be incorporated eventually in the ontology if the human being recognize it is a true fact, right? A true relationship.
I'm glad you say that because a lot of people that come from academic backgrounds sometimes they get in their head that the world works in one direction, you know, that there is a methodology that you apply and there are techniques that you must follow and they must have a particular width or depth or height. But the reality of the situation is when you go into a real world um, scenario, you may have or may not have certain elements that you need to create a comprehensive solution. So sometimes it makes sense to go from the top and then go to the bottom, or go from the bottom and then go to the top, or start in the middle and then go to the top, or whichever direction. But it's all based on the constraints of how much money is there, how many hours do I have in a day, how many skilled hands are able to tackle this simultaneously, and will the business give me the information I need to proceed? Will I get access to the database and the data? Am I allowed to see the data and the shape of it?
Yeah,
So
yeah, definitely.
there's so many other
And
considerations.
I agree on your on this specific point that you raised, Joaquin, about the academia, right? Because this is just uh, a way that I mean, a point that I can use to uh, reconnect to what I mentioned at the beginning of the conversation about the first perspective of knowledge graphs, right? I mentioned that it has been created since the beginning from philosophers of lawyers, but in that case, the main limitation was that they decided to model any detail of their knowledge domain, right? But without a direct and practical applications. So sometimes you have these uh, maybe not huge ontology, but they are really complex. They incorporate a lot of information in their relationships, but sometimes, in most of the cases, for practical business problems, all this huge and complex knowledge is not useful, right? Because sometimes you need to model just a specific subset of information that are useful only that are concretely useful for your specific purpose, right? In our previous meetings, we discussed it about data products, right? And we discussed about this idea of starting from the bottom. So basically, starting to understand your business problem and then create a model that could be a small ontology, a small knowledge graph that is practically useful for the problem that you want to solve, right? So this is the way in which we can use this technology in an effective way. Because I think that, I mean, this idea of the ontologies is quite old, right? But you cannot see many practical application of these ontologies, I would say, beyond the healthcare, because since the beginning they have been created to solve any problem, but in practice, actually, you cannot build something that is able to solve any problem, because you risk to do not solve anything, right? If you start from the generalization, if you start only from the modeling, and you don't have a clear view on the problems that you want to solve. So this is a main issue um, in the adoption of this technology. So we have to be careful in not start to model and then think about how I can use this model to solve my problem, but we have to adopt a different thinking that goes in the opposite direction. So you have to start with the problem and then just adopt the approach of modeling enough, right? So basically, I have modeled what I need in order to solve this problem. If the answer is yes, if the problem becomes more complex, then I can extend my modeling according to the new problem or to the more complex problem that I want to solve. Otherwise, if you start with the modeling, you risk to develop something that is not useful for practical reasons, right?
That makes perfect sense. Yeah, I mean, we talk to derive a particular objective, you know. I'm hungry, you're hungry, let's go get something to eat. But we're not saying, okay, before we have to go get something to eat, let's draw a map of the whole city. It's like,
Exactly.
no, I'm hungry, you're hungry, we want to eat. What do you want to eat? Okay, you want to go eat fried fish food, fried calamari. I want to go eat focaccia. So which options do we have available? This is the same way that a decision is made in a business setting. We want to accomplish this new product development, or the launch of this thing, or optimize or market share in a particular area. What areas of deficiency do we have in our business plan? Those are questions that
Exactly.
require precise answers.
Yeah. I would like to thank you, Joaquin, for this practical analogy, because I think that it fits perfectly, right, from what I introduced in this more theoretical way. So basically, this idea, I don't need the entire map because I would like to search something to eat or visit a museum.
I want
Then
to mangiare. I want to mangiare, man.
exactly. So I have to understand how to reach these places, right? Because in the specific situation I'm interested in, and then if I want to explore more, if I want to find some museums or some interesting place to visit, then I can expand my perspective, but from the eating place, right? Because I started the guide from there, right? So this is the way in which I can expand in a let me say iterative and with small updates my model, right? that's
Yeah,
uh,
now
that's uh, the idea.
we're full now, and now we're bored, and we're visiting this place for the first time. What is there to do? Do we want to go see the touristic things? Do we want to go see live music? Do we want to go to a comedy show? As you said, then we reason for the next decision making uh, situation. We need information to take a
Yeah,
decision. We need information to take a decision. And ideally, computerized systems help us derive richer information to take faster, more meaningful decisions. Um,
yeah, absolutely.
Let me tie this back into what we were talking about with the knowledge graphs and graph neural networks.
Yeah.
So, in the context of what we're saying here, I'm hungry, I'm going to go eat. I want to know what restaurants are available and the food type that I like. Where does this graph neural network technology play a role in that kind of situation?
Well, let's imagine an app that it's useful for suggesting you where you want to eat or which places you want to visit, right? The key idea is that you can employ graph neural networks for receiving recommendation and receiving an assigned score to this recommendation, right? Because when you become a user of the app, you bring with you your own properties, right? So basically, your age, your preferred food, your place where you live, and so on. And in this application, potentially you start to build a relationship with other users that can be your friends or that can be your
Hmm.
mentors or other type of relationships. So when you are model in this way, bringing your own properties and the connection with other users in the application, then a recommendation system can perform a sort of machine learn can adopt a machine learning approach to suggest you right some places to eat, deriving this information in a statistical way from your own properties and from the properties and the connections of your friends in this case. So
Okay.
this could be a practical way to use this technology.
So you are on the app, I'm on the app, and we have two other friends that are in the app. And we put on the app that we like to eat seafood. And we're of this age range and we're of this geographical location. So by proximity, it'll give us recommendation that the restaurants that we like to eat and we've logged we like to eat in. If a new actor were to come in and they were to have similar demographics, the graph neural network would be able to make a adequate recommendation based on the aggregate interactions within the system. Is that what it is?
Yeah, exactly, perfectly. So basically, and it is able to extract from a statistic point of view, right? In the sense that one of, as we mentioned, one of the powerful features, one of the most powerful features of the ontologies is that the ontology directly encode the information and potentially the rules. So let's imagine the situation in which the specific rule is that if I have two friends that like seafood, then I like seafood. So basically, the recommendation is the closest place in which you can eat seafood, right? But in this way, you encoded a rule. So if I have enough true friends, this establish the conditions for the recommendation. Graph neural networks are more similar to large language model in this sense because they derive this information statistically, right? So
Mm.
if in the entire graph I notice that a person that has two friends that like food select a food place, then potentially this could be a pattern that I can recognize and I'll apply to you, right? But the interesting thing is that in this way you can also predict unpredictable linking or relationships using the traditional inference of the ontology. So you can predict unexpected more than unpredictable, unexpected relationships, right?
But these the difference between, I'm glad that you said that it has a similar function mechanism to LLMs. They both model some sort of reality or some sort of domain, but graph neural networks is more so based on dynamic interactions, and large language models are based on static text that has been extracted and compiled and clustered and stored in some sort of structure that is not static, but it continues to move. Is that a better? I
I would say so. I mean, it's related. I would say this is a quite complex topic, but I will try to explain. This is related to the geometrical structure the model operate on, right? Because large language model operate on sequences, we can say, while graph neural networks operate on graphs, so basing on network structure. And this geometric aspect of the data is really important, right? Because, for instance, if you consider our other neural architectures like convolutional neural networks, they were extremely effective in modeling information that is structured as a grid, because images are represented as grids in a
Pixels, yeah.
digital form, right? Because you have the pixels and the number of the pixels. and you have multiple layers in your image if you have a colored image, because you have a value for the red, a value for the green, a value for the blue, right? So the idea is that can I exploit potentially the geometrical structure of the data that I operate on, right? So basically, large language models are really effective in process sequences, right? While graph neural networks are effective in processive structures. And some interesting research emerge also in this sense, right? I've seen that Google did a lot of research in this direction, in which they try to flat the structure representation of graphs. So basically, they try to describe a graph as a collection of tokens, so in a sequence, and they put this sequence to a large language model to understand what a large language model that operates on a flat representation of a graph is able to extract, right? So this is also an interesting way in which you can try to redefine the traditional nature of the data and then try to adopt the model that fits better on this new form of the data. Because you can take a network, you can take a graph, you can flatten the representation and provide the information within this graph as a sequence, and then you can take this sequence as input of the large language model and ask to the large language model what is able to extract, right? And it's interesting to see if it is able to extract some information that can be modeled only in a networked way. And they notice that right now it's not so effective, right? So basically, it's not able to understand the complex network structure from a flat representation of a graph, right? So this is another interesting research direction that is currently explored, right?
I think I think that the main takeaway from this conversation is that it's not that you focus on statistical AI techniques or you focus on symbolic AI techniques. It's that there is a combination of these techniques to employ a different aspects of reasoning with a computerized system so that you can accomplish a particular objective, whether it's for business, nonprofit, it doesn't matter. But sometimes you need to employ what is suited for large, brutish tasks, certain techniques, and for precise, very factual based tasks, other techniques. So I'm interested to see what kind of problem sets you work on in the future, given that you like looking at both sides of the coin and have a lot of experience solving these very complex problems.
Yeah, definitely, because this technology are evolving so fast. So basically, the opportunities in combining them in order to solve specific business problems will increase in the future, definitely.
Well, Giuseppe, I appreciate you giving us an hour of your time and breaking down these very complex ideas. I know I learned a lot, and I'm going to start digging deeper into graph neural networks now that you gave me this primer.
Great. Thank you very much, Joaquin. It was a pleasure have this conversation with you.